Today's Super Lab is Iod502, compare or combine data from a complex data presentation. Make sure you have the skill sheet in front of you as we go through it so that you can follow along as we are reading together as a class. We're going to get started by reading the introduction, the background together. We have a volunteer to read the background information. Thank you, sir.
Iod502 is the single most commonly assessed skill in the science ACT. Graphs and tables on the ACT often seem to be very complicated, but they really are not. All you need to do is carefully examine what they are trying to tell you. When you need to complete a skill like comparing data in a complex data presentation, just try to pick out what you know. Hint: most questions will tell you which figure you need to look at. Only use that one figure. Don't worry about the others.
Excellent. So a few hints that you should be aware of. First off, the question will always tell you where to look. That passage is the only passage that you should look at. Always just look at that one passage. You can answer it that way. Second thing is when we say complex data presentation, we're referring to passages that have more than 4 variables per either table or more than 4 variables per graph. That's what the word complex data presentation is, as opposed to simple data presentations which have 3 or 2 variables inside. So that's what we mean by complex data presentation. Let's get started off by reading the passage. As we read the passage, what we want to do is circle any words that you feel like are unknown to you. This is a great strategy to go through a passage so that we can make sure we identify any vocabulary that you're familiar with. So we're going along. Do we have a volunteer to read? Thank you very much. So we're going to have our volunteer reads. Please make sure that you have a pen or highlighter in your hand. You're either circling or highlighting any words that seem tricky to you. All right, whenever you are ready.
Earthquake produces
Seismic
waves that can travel long distance through Earth. 2 types of seismic waves are P waves and S waves. P waves typically travel 6 to 13 km over seconds, and S waves typically travel 3.5 to 7.5 km over a second. Figure 1 shows how P waves and S waves move and are refracted as they travel through different layers of Earth's interior. Figure 2 shows a seismograph, an instrument that detects system waves. Recording of waves and S waves are from an earthquake. Figure 3 shows in general how long it takes P waves and S waves to travel given distance along the surface from the earthquake focus and plane of the line report of seismic waves.
Good, yeah. So let's take a look at some of these words then. I guarantee there's at least 4 or 5, but there might be more than that. Want to give this one? Seismic. Seismic. Good. What's another one? Another word that came out that was a little tricky or confusing. Refracted. Refracted. One. Another word that's tricky or confusing.
Seismograph.
Seismograph. Here. Good. Another word that's tricky or confusing. Focus. Good. All right, those were the ones that jumped out of my head. Does anybody else have any others that we want to go through before we get going? All right, now this is a strategy that's very useful if you have some time. On the ACT, you're probably not going to be able to go through and try to identify every word that's tricky for you. But the reason why we're practicing this now is because most of these words are identified, described, or in the passage itself, or you can use context clues in order to figure out what they mean. All right, so the ones that I'm thinking of right now are like refracted. Refracted actually defines itself in the passage. When we say the word refracted, what we're actually looking at is bent. So as you look at a wave and you refract the wave, if a wave is moving in this direction and it hits something and is refracted, it will actually bend and change direction. That's what we mean by the word refracted. It'll actually bend and change direction. Another word, seismograph, is identified for us. It's an instrument that detects seismic waves. All right, it's an instrument that detects waves. When we say the word seismic, we didn't cover this one yet. Earthquakes produce seismic waves that can travel over long distances. Does anyone know what that word seismic means? Heard it before? Essentially, it's referring to interior of the Earth. So these are waves. These are energy waves that essentially travel through the inside of the Earth. All right, so that's what our term seismic means. So seismographs then are things that measure these waves. You've probably seen images of these before. All right, they're essentially a little needle on a little stick, and what they do is they sense the vibrations that are going on in the Earth. So it'll go along and just be, normally there's a little vibration all the time, but then all of a sudden here comes an earthquake and the needle starts to go crazy because the Earth under it is vibrating, and almost looks like a heart monitor sort of, but what it's actually measuring instead of heartbeats is it's measuring waves of the earth, so like the ground physically shaking, energy moving through the earth, and that's what a seismograph is. All right, these are things where you say like, oh, it was a 9.0 on the Richter scale for an earthquake, or they say like for a 7.0 earthquake. What they're measuring is what's called the amplitude of the wave, so how big the wave is from top to bottom. If it's really big, that's a huge earthquake. That's like it goes all the way up to 10, so it's like a 9.0 is massive. It would level a whole city. Whereas like we have 1.0 earthquakes all the time. You just don't feel them because they're so weak. All right. Actually, we have in Illinois we have an earthquake roughly once every 3 months. All right, and usually you don't even know it because the energy of them is so small that it just feels like a truck driving by. The last one is focus, and the term focus is defined for us again as the point of origin of seismic waves. It's essentially where did the earthquake start. All right, so there's our terminology. Let's start to take a look at some of the data. All right, we take a look at figure 1. Figure 1 is showing us the distance that waves travel in addition to what parts of the earth they hit. Some key focuses here are the word focus again, right here. So what this is showing you is that this earthquake in this example is starting right there. And you can watch the two different types of waves, P waves and S waves, travel from the focus. All right, now everybody who did their early Earth reading already and knows about the layers of our planet, this starts to make a little bit more sense. You see the mantle, the crust, the outer core, and the inner core. You can see how waves travel through these things differently. The last thing that you need to see on here is sometimes it can be a little tricky, especially if you have an old copy of the skill sheet in front of you, determining which ones are P waves and which ones are S waves. All right, S waves are the dotted ones, P waves are the solid ones. All right, so you can see up here, there's like little dots. That's the S wave, whereas this one is one solid line for the P wave. All right, and then the last thing to note is the degrees. So this is just how you measure distance around a circle. You just use degrees. So the earthquake, we're assuming, starts at 0 degrees here. Then they tell you what happens at 103, 142, and then it goes back around the circle again to the very bottom. This side over here should be 180, because it's the other side of the circle, and then it starts going back to 142, 103, and then back to 0. Figure 1. Figure 2 is the seismograph. All right, a key thing to notice here are the units. Every space represents a minute. All right, so this is just kind of a reprint of what the seismograph would look like. All right, what you'll notice is that this is the starting point right here. All right, so this is the starting point, not that point. Make sure you notice the earthquake starts there. That has tripped up many people that I've seen so far taking quizzes. Last but not least, we have figure 3. All right, if we take a look at figure 3, there's two different variables in this graph that the axes are showing you. Anyone just tell us what the x-axis is showing us in this case?
This is along our surface, vertical seismograph.
Yeah, perfect. So it's the distance that it traveled along the surface. The wave traveled from the focus to where it started. And then what is the y-axis showing us in this case?
Time to seismograph earthquake focus.
Excellent. So it's the time that it takes to reach the seismograph. So what we're doing here is we're comparing time and we're comparing distance on this graph using these two lines. All right, so what you would be able to do is a pretty simple problem then. If you knew how long the wave took, you could find, so you start with the time and you could find a distance. Or if you knew how far the wave traveled, you could start with the distance and find how long it would take. All right, that's the beauty of this graph. And you can do it for either type of wave. You can do it for S waves, which is this line, or P waves, which is this line. The one tricky thing about this graph that I want to point out is that typically what you've probably seen before is velocity versus time graphs. Distance versus time graphs, where the distance is on this side and the time is on this side. Please note that what we're looking at here is actually this, but inverted, so that distance is on the bottom, time is on the side. All right, so what we're going to do now is we're going to get started on the example question. Based on figure 1, what type of waves are received between 0 degrees and 103 degrees of the earthquake focus? All right, if we take a look at the 0 degrees, can anyone point out to us where we would find 0 degrees on figure 1?
All the way to the bottom.
All the way at the top. So that should be right here in 0 degrees. And then where would we find 103 degrees?
So they're right and left.
Yeah, so either right here or right here. It doesn't matter which one that we're looking at. So essentially what we're comparing here is what type of waves hit this area here. All right, what type of waves go on in that area. So anything that happens in this whole section counts. All right, so what type of waves are there?
Both P waves and S waves.
Both P waves and S waves. Now you can either look and notice that the dotted lines hit and the straight lines hit, or what else you'll notice is that it actually says right here that both P waves and S waves hit. All right, so sometimes they give you that data. All right. So what we're going to do now is we're going to get started on the guiding practice questions. If you are watching this video at home, you want to pause at this point, try to answer question 1, question 2, and question 3 on your own, and then press play when you answer them to go back to the answers. All right, so if you're pressing play now, you've already answered questions 1, 2, and 3, much like everybody in lab did right now. So let's go through the answers pretty quickly. According to figure 1, what types of waves are received in the shadow zone? Somebody point out for us where we see the shadow zone. Where is the shadow zone? Between what 2 degrees?
Between 103 and 142.
Good. Between 103 and 142, it's labeled right here. It's called the shadow zone. And what does it say about the shadow zone?
Neither P waves nor S waves receive at
Seismograph. Good. Yeah, so this doesn't get either type. You can either see it in the passage. You'll also notice that in this area right here, none of those lines are getting through. All right, essentially the way that the waves are bent is that it's impossible for any wave to hit these 2 specific points after an earthquake. All right, now there's 2 shadow zones because that'll come up later. Please note that there's a shadow zone on essentially each side of the core from where the earthquake was. That'll be important later. All right, so this one should be none. Moving on. Number 2. Based on figure 2, how long does it take from the time of the earthquake for the first P waves to be received? What do we think? How'd you get 6 minutes? Good. So it says each space is 1 minute over here in the key. Now the tricky thing here is where does the earthquake start? Yeah, it tells you where the earthquake starts, which is right here. All right, don't get caught up and use this spot over here because that's not right. Make sure you count from here and you count 1 minute, 2 minutes, 3 minutes, 4 minutes, 5 minutes, 6 minutes to where this one is right here. All right, so the answer here should be 6 minutes. Don't forget to use it. Next question. All right. According to figure 3, which type of wave, P or S, travels faster? Now, this is a tricky one if you're using your old knowledge of this graph. All right, the old versions of this graph might lead you astray. What do you think?
P waves.
P waves. How'd you get P waves?
I looked at the distance thing and just like any random one, I chose 4,000, and it took 7 minutes for the P waves to get to 4,000 kilometers and like 12-ish minutes for the S waves.
Excellent. Your old versions of this graph where it was distance versus time, the line that was on top was always the faster line. All right, the one that was on top of the 2, like this one right here, would always be the faster line. But since it's inverted, it's actually the lower line in this case that's the faster one. And your explanation was perfect. It covers more distance in less time. All right, so if you make a look at the same distance, so let's say 5,000, it takes the P waves only 8.5 minutes to go 5,000 kilometers, but it takes the S waves 15 minutes to go 5,000 kilometers. So P waves must be faster. All right, at this point, we want to move on and start to take a look at the individual self-practice questions that are about figure 1. If you're watching this video at home, you want to pause at this point and answer questions 4, 5, 6, 7, 8, and 9. You press play when you are ready to go through the answers. All right, at this point, if you are pressing play, that means you've answered questions 4, 5, 6, 7, 8, and 9, and you're ready to go through the answers. First off, question 4. Which type of, or types of waves are received on the side of the planet exactly opposite the earthquake focus? We take a look at the graph. Where would be exactly opposite the focus?
P waves,
How'd you get P waves?
because I looked at the top are there.
Excellent. If we go directly opposite, the only thing directly opposite of where the focus is are P waves. Boom. Right, answer here should be P waves. What about which types of waves cannot travel through the outer core of the planets?
S wave.
How'd you get S waves?
Because if you go to the outer part, outer core, the S waves stop right at that line.
Excellent. You see these S waves here, they stop. Perfect. They can't travel through. All right, so the ones that can't travel through are S waves. What about number 6? Which type of wave, P or S, travels further from the earthquake focus?
P wave.
How did you get P waves?
Because you go right down from 0 where the earthquake starts, and P waves are the only ones that went through.
Excellent. P waves are the only ones that went through. This is actually very similar to question 4 in how you do it. Just it's a different way of asking pretty much the same question. All right, now we get to question number 7 about different seismographs at different stations. If you have a seismograph at 20 and a seismograph at 120 degrees from the focus, which one would receive more S waves?
20 degrees.
Why do you say 20 degrees?
Because if you guesstimate, you put like around the area of 20, which is closer to the 0, the heights there, or like something there, and then whatever's closer to like 140 or 120, so between 142 and 103, put like the next there, and see which like waves hit that area the most.
Excellent. So you can estimate 20 degrees because it's closer to 0 than it is to 103. You can estimate where 120 would be because it's between 103 and 142. The one at 120 is actually in the middle of the shadow zone, so nothing hits it there, which means the one that has to get more waves is the one at 20 degrees. All right, what about the next one? Which seismograph station will receive more P waves? One at 140 or one at 144? How would you get this one?
Look at, go past 142, then cross right there, and then
So
144.
Right, so right past 142 would be 144, and where would we find the other one we're comparing it to is 140, so where would 140 be?
Oh, right between 142 and 103.
Excellent, right on the other side there. Which one's in the shadow zone?
140.
So which one gets more waves?
140.
Boom. 144 should get more waves because 140 is in the shadow zone. Last but not least, this one could be tricky if you didn't catch this one. All right, the question says, after an earthquake, how many total degrees of the planet do not receive any type of seismic wave? There's 2 things you have to keep in mind here. We're looking for do not receive any type of seismic wave, and we're looking for the total degrees. All right, how would we answer this question?
The answer is 70 degrees because you look at the shadow zone between 103 and 142, so I just subtracted them from each other and got originally I got 39, but then my group said to add them because it's total. When I added 39 to 39, I got 70.
Excellent. So if you do the initial subtraction to find out how many degrees one shadow zone is, you would do 142 minus 103, and that will net you 39. What you have to remember is that there's not just one shadow zone. There's 2 shadow zones, which means that this 39 is here, also over here, which means you have to double. You double 39, and the final answer, 78. All right, now what you want to do is we're going to answer questions 10, 11, and 12 based on figure 2. If you're watching this video at home, you want to pause at this point and answer questions 10, 11, and 12. Don't push play until you're ready to go through the answers. All right, at this point, if you are pressing play, you are ready to go through the answers for questions 10, 11, and 12. Let's first get started off with question 10. Which types of waves would travel fastest through the planet? How would we get this question?
You gotta go. Well, I said P waves
Why did you say P waves?
because P waves come first on the seismograph.
Perfect. Nice. Since P waves come first, so here's where it started. You notice P waves hit first and S waves hit second, so P waves must travel faster. All right, what about the next one? How much longer did the S waves take to reach the seismograph station than the P waves?
I said 4.5 seconds.
get 4.5 minutes.
Because we start at the first few waves, and then we count the
2, 3, 4. And you notice this one is about halfway through. So it'd be about 4.5 minutes. Don't forget your units. Units. The last one, number 12. Which type of wave, P or S, is stronger when it reaches the seismograph?
I said S waves are stronger for the fact that it has, when it reaches the seismograph, it has more
Amplitude. Yeah, so the amplitude is higher for these. The amplitude is higher on these waves. It goes all the way from here to here, whereas the P waves only go from there to there. All right, so the S waves are the stronger waves. Fantastic. All right, it's time to move on to our last 2 sets of questions. At this point, if you are watching this video at home, pause here and answer questions 13, 14, and 15 about the passage in Figure 3. I'll give you a hint. Question 15, you also need to look at Figure 2, in addition to looking at Figure 3. Press play when you're ready. Check your answer. All right, you are pressing play now. You have already answered questions 13, 14, and 15. So let's go through the answers together. Number 13, after 10 minutes, how much further have P waves traveled than S waves? How would you answer this particular problem?
Okay, so I would look at 10 minutes on P waves and S waves, and then I will like find the distance, which was about like 3,000, and in between 6,000 and 7,000, which was about 6,500. Then I'll subtract the 2, and it'll give me 3,500.
Excellent. So the 6,500 kilometers right here, subtracted from the 3,000 kilometers right here, gives you an answer of 3,500 kilometers. Nice. Question 14. How much longer would S waves take, or how much longer would it take S waves to travel 7,000 kilometers than P waves?
We said 8 minutes.
8 minutes? How do you get 8 minutes?
Well, you gotta go to 7,000 AM, then go up. You're going, stop at your first one, and go over and see what time it is.
That's close. Yeah, that's okay.
Then keep going, keep going down. And stop, and that's, so then you have to do the subtraction. And that's at 19.
Great. So you do 19-ish minus 11-ish, and you should get somewhere around 8 minutes. Last question. Trickiest one. You need to use Figure 2 in order to do something. All right. As we take a look at this question, just keep in mind always what it's asking you for. It's asking you for how far this is. That's a distance. You have to find the distance. All right. How would we go through this problem?
So I looked at Figure 2, and I noticed the first wave thing was at 6 minutes. So then I went to 6 minutes on Figure 3, and then I noticed it was like around 3,000, and because it was P waves that hit first, and then yeah, so my answer is like 3,000.
Great. So in order to kilometers, good. Units. So in order to see this, you have to see that distance is on this axis down here, which means that you somehow need to get to this point on this axis. But the only way to get to this distance is you have to know a time in order to find the distance, like we were doing in the last 2 practice problems. Where do you get a time from? That's where Figure 2 comes in. All right, the seismograph is sitting at a station, so all you have to do is figure out how many minutes it takes for the P waves to get there. Starts here and it goes 1, 2, 3, 4, 5, 6 minutes for P waves to hit the seismograph. You go back to the graph, find 6 minutes, trace it over to P waves. That means it took about 3,000 kilometers worth of distance. All right, at this point, we have just 3 questions left, and you are good to go, 16, 17, and 18. If you're watching this video at home, now you want to pause and answer questions 16, 17, and 18. Good luck. If you're watching this last video clip, that means that you have answered questions 16, 17, and 18 and are ready to go through and take a look at the answers. So for questions 16, 17, and 18, these are questions from actual ACT that are using the same skills that we've already used for the last couple of minutes. Question 16. Figure 1 shows that a seismograph located at a point 125 degrees around the Earth from an earthquake focus would receive which types of seismic waves, if either, from the earthquake? And again, we've already answered this question before, not necessarily in this wording, but what we're looking for is what type of waves at 125 degrees. We find 125 degrees, we think about here. What types of waves? Well, it's the shadow zone, so we want to see either type of wave. According to figure 2, which the following statements best describe the relative amplitudes of the first P waves to arrive at the seismograph and the first S waves to arrive at the seismograph? The amplitude, so this is one of those kind of questions where you need to find the second half of the sentence that makes it work. So the first half of the sentence is the amplitude of the first P waves to arrive at the seismograph is, so you have to use that first half, the second half makes it work. Smaller than the amplitude of the first S waves, larger than the amplitude of the first S waves, non-zero, and the same as the amplitude of the first S waves, zero, and as is the amplitude of the S waves. So if we take a look with the P waves, with that amplitude, S waves with that amplitude, the P waves are bigger. I'm sorry, the P waves are smaller, which means if we take a look at the question, we really want to use the second half of this sentence right here. So that the sentence says the amplitude of the first P waves to arrive at the seismograph is smaller than the amplitude of the first S waves to arrive at the seismograph. The amplitude is smaller here. Our last question, question 18. Based on figure 3, for a given seismograph, the time elapsed between the arrival of the first P wave and the arrival of the first S wave from the earthquake focus 10,500 kilometers away would most likely be. And so what you want to do here is you want to extrapolate out. What extrapolate means is you look at the data and you try to see where the data would head. Because if you look, this ends at 10,000 kilometers, but we need to get to 10,500 kilometers. Right? So in this case, what we're looking for is the time elapsed between them, essentially like right here, right, at about 10,500. So if you trace this up, all right, and we see, this line would kind of keep going like this, and this line would kind of keep going like this, and we have a point here and a point here. Trace them over, and this would be somewhere around 25. This would be somewhere around 13. All right, so 25 and 13. You definitely would see it be more than 10 minutes. All right, you have successfully answered all of these questions. If you feel like you understand it, you are ready to take a quiz. Good luck on your skill sheet.